Hey folks, today's topic is looking at rational functions. So we spent a lot of time doing polynomial functions. And then the other set of functions that are really helpful, especially when it comes to the calculus, are these rational functions, because we get these sort of weird stuff that happens. We've got these asymptotes, and we also have this little point that's missing, which we call a hole. So if I already graphed this on my calculator. So what's crazy about this is you can't tell this unless you dig into the function algebraically to figure out that if I trace, like, look, let's say I trace to 1. Okay, we have a y value of 1/2. All right, that makes sense. Let's say I trace to 2. I have a y value of -1. Let's say I trace to 3, and I don't have I don't have a y value at all. Well, that makes sense. We have this thing that's called an asymptote there. So this is kind of that shifting stuff that we talked about back in transformations in Unit 1. But what's crazy about this, asymptotes are pretty, dang it, excuse me again. Asymptotes are pretty easy to figure out because you can really see them on the graph. But this little tiny hole that's missing is not. If I trace to 4, so you look, there is no y value at 3. If I go to 3.1, there's a y value. If I go to 2.9, there's a y value. But if I go to 3 itself, there's nothing there because there's an asymptote. There is no actual function value. Same thing happens when I trace to 4. Now, you can't tell that by looking at the picture. 1, 2, 3, 4. I go up to the graph. It looks like it's just fine. The problem is there's this little tiny hole missing. If I go to 3.9, there's a point. If I go to 4.1, there's a point. And so there's literally just one little dot missing from this graph, and it's missing at 4. So how do we figure out that? How do we know this? How do we find this? Well, that's what we're going to talk about when we look at analyzing this function. Well, let's start off talking about, since HAs come first, horizontal asymptotes. Let's talk about how we find those. So there's 3 scenarios for finding out your HAs. So basically, when you're looking for an HA, you're trying to see what happens as x approaches infinity. You might remember that notation from our limit stuff we did earlier. So I want to look at this function, and I want to just kind of focus on the pieces that are most important. And so if you remember when we did end behavior back in 2.2, this numerator gets dominated by the first term. I mean, think about it in terms of, remember, we're picking x's that are close to infinity. And I like to think about it in terms of money. Let's say you had a million, let's say x stood for let's say $1 billion. Now we're taking $1 billion and we're timesing it by 3. And then you're losing $9. Does that 9 have much of an impact? No, of course not. I mean, does it change it? Yes. But it changes it so inconsequentially compared to the number itself that it almost has no impact. Same thing on the bottom here. This number is in the billions, -2 times a billion. But this is a billion times a billion. This is a huge, huge number. So when I take away 2 billion from a billion billions, it's really not that big. And then you take away $3 from that, it's really not that big at all. So this turns out to basically look like 3x over x squared. Well, 3x over x squared is much easier to manage than this. So 3x over x squared turns out to be, if the x's cancel, 3 over x. Now think about what's happening here. I'm putting a huge, huge number in for x, something massive. Like, think about it. If you took 3 pizzas and you divided those pizzas by everybody in the classroom, how much pizza would you get? Okay, you could kind of picture it. What if we took those 3 pizzas and divided by everybody who lives in Fruitport, not just in this classroom? You're going to get a lot smaller amount of pizza. Let's say we took these 3 and divided by everybody in the state. Let's say we took and divided by everybody in the country or everybody in the world. What's happening to the amount of pizza that you're getting? Essentially, you're getting closer and closer and closer to nothing. So as x gets bigger and bigger and bigger, when you divide by a really, really big number, your answer gets smaller and smaller and smaller and heads towards 0. In this scenario, your HA, or your horizontal asymptote, has the equation y equals 0. Now we're going to find a shortcut at the end of all of these, but for now, let's just move on to the next situation. Remember, here we are again. What's the one that matters the most on the top? The 3x squared dominates so much that the other ones kind of fade away as we go off towards infinity. Same thing with the bottom. We have 4x squared on the bottom that dominates. So now I have 3x squared over 4x squared. Now notice I'm not writing equal signs here because these are just saying that they behave similarly to the next expression. So the x squareds are going to cancel out and we're left with 3/4. Now that kind of makes sense. Our graph in this case levels off, has a horizontal asymptote of y equals 3/4. Because think about it, no matter how big the numerator gets, the denominator is getting equally as big. So these 3 and this 4 multiplier out front is what this graph is going to level off at. As this grows, huge, this is getting just as huge. So the 3 times that massive number and 4 times this massive number is going to just leave you with the 3/4. And then the last scenario is when we have, well, I don't want to ruin it yet, so I'm not going to say it. Let's try to clean this up. So we're going to look first. X cubed dominates on the top. 2x squared dominates on the bottom. X cubed over 2x squared. X squared cancels with x cubed. I get x over 2. Now this time, the huge number, x is getting to a very, very, very big number. That big number is on the top. So some massive number divided by 2 is going to become some other massive number. Now it's half as big, but as this number gets big, I mean, what's infinity divided by 2? It's still infinity. So in this case, our HA doesn't exist. We would say there is no HA. The HA is none. So what's the shortcut? What's the quick way that we can just look at this and we can identify right away which scenario that we're in? My advice is take a look at how many x's you have in each scenario. What do you notice? Well, hopefully you notice that in this case, there are more x's on the bottom. More x's on the bottom. In this case, they're equal x's on the top and on the bottom. And then over here, we have more x's on the top. So when I'm trying to figure out my HA, all I really do is I care about the most powerful term on the top compared to the most powerful term on the bottom. If there's more on the bottom, if there's more x's, notice I'm not talking about coefficients, I'm talking about exponents. So if there's more x's on the bottom, your graph will level off at 0. If there's more x, if it's a tie, your graph will level off at the coefficients, 3 over 4. If there's equal x's, it's just the coefficients. And then if there's more x's on the top, it was x cubed over an x squared. That means your graph is going to go off towards infinity, so it's not going to level off at all. So let's go back up here. How did we figure out the HA again? Well, we looked at the most powerful term on the top compared to the most powerful term on the bottom. And 99% of the time, they're going to be written in that format so that you can, where the first term is the term that we're talking about. So I'm going to have you circle these two and draw a little arrow that says HA. You can figure out your horizontal asymptote by comparing leading terms. So over here in our picture, this is what we call an HA, horizontal asymptote. All right, so the vertical asymptotes. Well, the vertical asymptote is tough to see just by looking at the equation. But what you can do is you can take that equation and you can break it down. So what I'm going to do is I'm going to factor the numerator and I'm going to factor the denominator. So let's see. 2 times 12 is 24. That makes 11, negative 11. That's negative 3 and negative 8. So the numerator factors into 2x and x. I need to make a negative 8, so that's going to be the negative 4. I need to make a negative 3. Then I'm also going to factor the denominator here. So that's 1 times 12 is 12. That makes a negative 7, so that's negative 3 and negative 4. So this then factors into x subtract 3 and x subtract 4. Well, look at the equation for our vertical. Oh, sorry, I guess we should have compared the HA. Let's get that out of the way before we move on. So the HA, 2x squared over x squared, which scenario does that fall into? Are there more x's on the top, bottom, or tie? Well, it's a tie. And when it's a tie, it goes to the coefficients. So the coefficient is 2 over 1. 2 over 1 is 2, but you're writing an equation. So don't forget that you have to write y equals. You do not get partial credit if you just write 2. We have to write it as an equation. So now let's try to look at the picture and figure out where our VA is. Well, the VA is the vertical line. So let's draw a little arrow here. This is what we call the VA, the vertical asymptote. It's the vertical line that separates the two branches of our hyperbola. So our vertical line goes 1, 2, hits at x equals 3. Looking up at our equation, did you notice anywhere that we have something that we could use to turn into an x equals 3? Well, hopefully you recognize this. If I ZPP'd this, I would find x equals 3 as my 0, which turns out to be the same place where my asymptote is. Let's finish this and then we'll come back over here and talk more about how to find them. I'll save that for a minute. All right, next up, we're going to look at what happens when, where's this hole? This one little spot that's missing. Well, the location of this hole, now we don't want to write just the x number. We're going to write when, because the graph doesn't have a y value. So this is, the hole occurs when x equals 4. In the equation, do you notice anywhere where x equals 4? Well, look at what happens. What did you find on the top? One of my factors was x minus 4. The other factor on the bottom was x minus 4. When those cancel out, that creates the hole. So when two pieces cancel out in the numerator and denominator, that creates a hole. And then, what would be a good color to go with next? Maybe yellow. Zeros. Zeros are the places where our graph hits the x-axis. These are our solutions. We've spent a lot of time talking about zeros. These are also known as x-intercepts. So the location of our 0 is a coordinate pair. This is 1.5, or I'm going to write it as a fraction, 3/2, 0. And then last characteristic that we're going to focus on is the y-intercept. And right here, we have a y-intercept. Y-intercepts always have x values of 0 and a y value in this case of 1. So how do we find all these things without being given the picture? Because on the test, I'm going to have you give you the equation, and you've got to find all these pieces. Well, the first thing we noticed is that if you compare the leading terms, you can figure out where the HA is. More x's on the top, more x's on the top, more x's on the bottom, or a tie. More x's on the top, you would write HA is none. More x's on the bottom, you would write HA is 0. HA y equals 0. And then if it's a tie, it's y equals whatever your coefficients are. My coefficients were 2 and 1 in this case. You have to memorize these three. I'm going to make a cheat sheet or let you put this on the back of your parent function sheet. But you do have to remember the three different scenarios. Okay, where does a VA occur then? A VA happens when anything in the denominator that doesn't what? This was in the denominator, but why was that a whole and not a VA? Because it canceled out. So denominator, no cancel. When did we have a whole? What created a whole in our picture? That's when we had it in the numerator and denominator. You had to have the same factor in the top and the bottom. Numerator and denominator. In other words, what had to happen to them? They had to cancel. Where do we find our zeros? Well, we had a 0 of 3 halves. Do you see that anywhere up here? You see a piece that makes 3 halves. Hopefully, you recognize this piece when I ZPP it ends up being 3 halves. This creates our zeros. So where do we find a 0? So we had something in the denominator that didn't cancel. That created a VA. Something in the numerator and denominator, which means it will cancel, creates a whole. And then if it's only in the numerator and no cancel, that creates a 0. And then last but not least, our y-intercept. Our y-intercept can be found by plugging in 0. By plugging in 0 for plugging in 0 for x. So if I put a 0 in, remember all y-intercepts have a 0 for their x. So if I make this 0 and I make this 0, what am I left with? 12. If I make this 0 and I make this 0, what am I left with? 12. And what's 12 divided by 12? That's where our 1 comes in. So I can compare constants, we call those. Constants are any terms that don't have x's. Now, usually kids do pretty well with the first one and the last one, finding the HA and the VA, because we can compare that's given right away in the equation. And it gets a little bit confusing how to remember these three. So there's a nice little kind of setup that you can show. You're going to have, what would be a good color here? So if I'm going to have one of 3 scenarios. So if you have something in the denominator that doesn't cancel, that means that this on the bottom, when I put 3 into this on the bottom, I'm going to get a 0 on the bottom, but I'm not going to get a 0 on the top. So this is what it looks like when it's no good. That means a 0 on the bottom. The numerator and denominator, they cancels. That means when I put 4 into this function, I'm going to get a 0 on the top and I'm going to get a 0 on the bottom. 0 over 0 creates a whole. And then the numerator that doesn't cancel, that's when there's a 0 on the top and the bottom doesn't cancel out. So that turns out to be okay. All right, so let's take a look. Let's try this now. I've done a lot of talking there. Probably a lot of it didn't connect yet, but at least we now have this list that we can refer back to when we're trying to analyze one of these rational functions. So let's go through our list. HA, how do we find the HA? Compare leading terms. So x squared over x squared. More on the bottom, tie, or more on the top? Well, it's a tie. That means it goes to the coefficients. This is a 1, this is a 1. So my HA is y equals, don't forget the y equals 1. VAs. VAs are things in the denominator that don't cancel. Well, I don't know what's in the denominator that doesn't cancel until I factor this. So I want to factor the numerator and denominator. I'm going to just factor it. If you don't know how to factor, you and I need to meet. You need to go back and watch one of the videos from section 0 or come in after school and I can help you out. Okay, so now I've got this factored. VAs are things in the denominator that don't cancel. So I'm going to highlight this first by seeing what does cancel. X plus 2 and x plus 2 do cancel. So the thing on the bottom that doesn't cancel is x minus 3, which I now want to ZPP, and I get x equals 3. The whole is where numerator and denominator that does cancel, x plus 2, but then you need to ZPP it. And the way we write the whole, we want to say when x equals whatever that x value is. So when I ZPP that, I get when x equals negative 2. Zeros are everything in the numerator that doesn't cancel. Numerator, no cancel. So the thing in the numerator that doesn't cancel is x minus 1. I ZPP that. Now, a 0 is a point, so it should be written as a point. When I ZPP this, I get x to be 1, and the y would be 0. And then y-intercepts, compare your constants, or you can think about it as all y-intercepts start with a 0 for x. So put a 0 into your equation. That's gone, that's negative 2. That's gone, that's negative 6. So what's negative 2 over negative 6? That reduces to be 1/3. All right, I'm going to encourage you to pause here and see if you can try to do example 2b on your own. All right, let's see how you did. So, HAs, we find those by comparing coefficients. X squared over x squared, so it's a tie, so it goes to the coefficients. 2 over 4 is 1/2, so my HA is y equals 1/2. VAs, denominator no cancel, so I have to figure out how this factors. So that's 12, that makes 7. So I've got to make a 4, a negative 4, and a, nope, that's not going to work. Yeah, but it's got to be a 2, silly. Minus 2 plus 3. And this is dopes, plus 2x plus 3, 2x minus 3. Anything cancel? Yes, sirree, Bob. Okay, so VA denominator no cancel. X equals 3/2. Whole, thing that does cancel. When x equals negative 3/2. 0, numerator no cancel. That's the x number. The y value would be 0. All y-intercepts have 0 for x. So that would be 0, 0, 6, 0, negative 9. 6 divided by negative 9 reduces to be negative 2, negative 2/3. I have 3/2 in my notes, but I was wrong. Negative 2/3. I'm going to encourage you to pause. Try to do the next one on your own. Let's see how you did. HA, compare constants. Whoa, this one's a little bit different. So there's more x's on the bottom. I always think about more x's on the bottom is like pulling you down to the ground, pulling you down to 0. So my HA is y equals 0. My VAs. VAs are things in the denominator that don't cancel. I first have to factor this to see if anything cancels. And if I look, And if I look, 6 and 10 both share a 2. So I can factor out a 2. That's 3x minus 5. That's a cube, so I know right away I can do a factor out. Everything has an x, so I'm going to take that out. That's 6x squared minus 13x plus 5. And now I can factor again 30. That makes 10. That's 10 and 3. 10 and 3, so there's a 2 and a 3. That makes the 6. A 10, I need it to be negative, and the 3, I need to be negative. So does anything cancel? Yep. All right, now, VAs. Things in the denominator that don't cancel. There are 2 things in the denominator that don't cancel. That means I have 2 VAs. If I ZPP x, it would just be x equals 0. If I ZPP 2x minus 1, I would get x equals 1/2. Whole is anything that does cancel, so that's when x equals, and then I would ZPP this, so that would be 5/3. Zeros. Anything in the numerator that doesn't cancel. Now you might say, well, wait, 2 didn't cancel, so I have a 0 at 2. That is not quite true. And let me show you why. If I took, remember, we're ZPPing everything. If I took 2 and I set it equal to 0, does that have a solution? It doesn't even have an x. How could you possibly find that? So there is nothing, none. There are no, this doesn't have a solution. There's nothing in the numerator that doesn't cancel that I can solve. And then y-intercept, I compare, put 0 in the top and put 0 in the bottom. So when I put 0 in the top, I would get -10. When I put 0 on the bottom, I would get 0. What's -10 divided by 0? Ooh, that's bad news. -10 divided by 0 is undefined. So this graph didn't have a x-intercept or a y-intercept. All right, last one. I encourage you to pause. Give it a try. All right, let's see how you did. So the top, I can do a factor out. They both have a 3 and they both have an x. So that's 3x and x squared minus 9. Oh, my math voice is screaming here. Do you see it? That's dopes. So that's 3x, x plus 3, x minus 3. So look, this goes back to section 2.3. If you can't recognize your factoring moves, you're dead in the water. You have to go back and make sure that you have those moves memorized and that you can recognize them when they come up. Okay, so this is a factoring 60, that makes 11, 15, and 4. So that's 5x and x. I need a 15, and I need that 15 to be positive, and then I need a -4. All right, anything cancel? X plus 3, x plus 3. So HA, notice this time I factored before I did my HA. When I do my HA, I got to go back to the original. So in this case, there's more x's on the top. I think about this, more x's on the top means that this is going to float away. And if you're float away, you're going off to infinity. So there is no leveling off. There is no HA. VAs are things in the denominator that don't cancel. So we have something in the denominator, ZPP it. X equals 4/5. The whole is when things cancel. So I have things canceling at x plus 3. So we have a whole at -3. Zeros are things in the numerator that don't cancel. So this time I have 2 zeros. There are 2 things that don't cancel. If I ZPP 3x, that would say 3x equals 0. And when I divide by 3, I get 0. So 0, 0 is one of them. And then the other one, when I ZPP 3, I get 3, 0. And remember, y-intercepts always have a 0 for x. So if I put a 0 in here, I get a 0 on the top and then a -12 on the bottom. So this time when I plugged in 0, I got 0 over -12. Is 0 over -12 okay or no good? That one's okay. All right, a lot of information there. Now this is going to lead in. We're going to hit this again next time when we try to graph these. We're going to try to make this sketch by hand based only on the equation. But if you don't have a lot of practice with these tricks, you're going to be up the creek. So make sure that you give the homework a try before next notes. Good luck.